Hi friends, I'm Priyanka from Achievers Hunt, and today I'm back with some basic concepts of chemistry wherein I'll be answering your exercise questions and I'll be basically explaining them to you. So in our previous three video lectures, in detail discussed the theory concept of this particular chapter, this particular topic, and we have gone through the major formulas that are required for you, as well as we have gone through some examples that will be asked for your exams. So, in this particular video, we'll be focusing majorly on all the exercise questions which are there in your NCRT textbook. So, I hope you like the demo lectures that we gave. We will be covering all your topics in such comprehensive manner. We'll be providing the ebook to you for your reference also from Achievers Hunt. So it is my kind request to you, as and when I'm discussing, as and when you're going through a video, kindly look into the ebook material for more examples. Kindly look into the notes which is being provided in your ebook material, and take the practice tests which are being provided from Achievers Hunt, because this is going to help you in the long run. At the same time, as students, I participate in as many tests and the state level quizzes that are happening, so that you're well prepared for your NEET and JEE as well as CET exams. So, without any further delay, let's get started. Question number one: calculate the molar mass of the following. So, we have three questions which are there for us. We have water, we have carbon dioxide, and we have methane. So, remember, molar mass is nothing but molecular mass is your molecular mass. Molar mass is molecular mass expressed in grams per mole. How do you calculate molecular mass? In a second video, I have explained that molecular mass is nothing but sum of your atomic masses. So, see over here, it's very easy for you all. You have water, you have carbon dioxide, and methane. However, I will work out the first one for you so that the other two we can practice together. So, it's my kind request, since most of these questions here are numericals and objective type of questions, kindly pause the videos for repetitive type of questions. Work it out yourself and then see if your answer and my answer is matching. So, in case of water, atomic mass of hydrogen we know is 1.008 U or AMU. Now, this value is given in your question. We take this value when it's given in your questions. If it's not given in your questions, you can simply take as 1 AMU or 1 U. Similarly, atomic mass of oxygen is 16.00 unified mass. Now, since in our molecule we have two hydrogen atoms, we do 2 into the atomic mass of hydrogen plus 1 oxygen is there, 1 into atomic mass of oxygen. So on solving we get 18.016 grams per mole. Remember, for carbon dioxide, carbon has an atomic mass of 12.01 U and oxygen I told it's 16.00 U. So molar mass will be in CO2, since only one carbon is there, it will be 1 into 12.01 plus, since two oxygens are there, 2 into 16.00 is nothing but 12.52, which gives us a total of 0 grams per. Okay, so please pause the slide and work it out yourself and then cross check your answers. In case of methane, carbon has an atomic mass of 12.01 U and hydrogen has an atomic mass of 1.008 U. So since only one carbon is there, its molar mass will be 1 into 12.01 plus, since 4 hydrogens are there, 4 into 1.008. So I get 12.01 plus 4.032, which gives me 16.02 grams per. So it's a very easy question, very straightforward question. I hope it's clear to you. Let's move on to the next question. Second question: calculate the mass percent of different elements in sodium sulfate. So sodium sulfate, they have given you the formula. It is Na2SO4. Okay, and we know that mass percent formula we have studied in our previous videos. That mass percent is nothing but mass of element in 1 mole divided by molar mass into 100, correct? Now, using this formula, let us see what are you supposed to see? Different elements, the mass percent of sodium, mass percent of sulfur, mass percent of oxygen. Okay, so let's quickly see how we can solve this particular question. Now, first thing we do is we need to find the molar mass of sodium sulfate. So we are given that sodium is 23, sulfur is 32.07, and oxygen is 16.00 U. So our molar mass will be 2 into 23.0 plus sulfur only 1 is there, so 1 into 32.07 plus 4 into 16.00. That is nothing but 46.0 plus 32.07 plus 64.00. So we end up getting 142.07 grams per mole. Once we have found the molar mass, see everything is there, we have to just substitute the value. Mass of sodium. So mass percentage of sodium, if you're seeing, since we have 2 sodium atoms, okay, that is the reason why I do 2 into 23 divided by molar mass 142.07 into 100. So 46 by 142.07 into 100 is nothing but 32.37%. Similarly, only one sulfur is there, so I get 32.07 divided by 142.07 into 100, which is 22.57%. And for oxygen, since 4 oxygens are there, 4 into 16 is 64. 64.0 divided by 142.07 into 100, which is 45.06%. Now remember, this question can be twisted and asked which element in the given compound has the highest mass percentage. Now we have to do this, the method will be the same, but the highest mass percentage here is for oxygen. Similarly, they can ask which element has the lowest mass percentage. That will be for sulfur. So either way, the main formula that you need to remember is for mass percentage. Number 3, determine the empirical formula an oxide of iron which has 69.9% of iron and 30.1% of oxygen by mass. So remember when I told you we are finding empirical mass, what we have, whenever they have given you a percentage, okay, consider that you are finding for 100 grams. Okay, so 69.9% of 100 grams is nothing but, if I see for iron, okay, so in Fe, if I need to find the mass of Fe which is there in that particular 100 grams of that compound, 69.9% of 100 grams is nothing but 69.9 grams itself. Similarly, for oxygen, it is 30.1 grams. So remember how we found our empirical formula. First, what do? We find the number of moles. After we find the number of moles, what are we supposed to do? We are supposed to divide it by the lowest number of moles so that we get whole number. Till we get a whole number. And then comparing the whole number ratios, we are going to express the empirical formula. So, as I said, whenever empirical formula and percentage of mass is given, consider it for 100 grams. So, assuming 100 grams of the compound, 69.9% is nothing but 69.9 grams of iron and 30.1 grams of oxygen. Okay. Now, how do we find moles? Moles is equal to given mass by atomic or molecular mass. Since it's atoms here, we are finding atomic mass. Atomic mass of iron is 55.85 U and atomic mass of oxygen we know is 16 U. So finding out, we get moles of iron is 1.251 and moles of oxygen is 1.881. In step 2, what are we supposed to do? We are supposed to find the simplest ratio of these moles. So what are we supposed to do? I told the lowest moles that you have, you divide them with all the values that you have got. So for iron, I get, so iron is to oxygen, I can just write it as 1.251 divided by 1.251 is to 1.881 divided by 1.251. So first you find the number of moles. Now we have to convert these moles to the simplest ratio. So 1.251 divided by 1.251. How to convert them to simplest ratios? Divided by the lowest value that you have got. Suppose you had a value less than 1.251 divided by that value. Okay, so I get 1 is to 1.5 as my ratio of iron to oxygen. Now remember, when we spoke about the second law, we said that when atoms combine to form a compound, they do so in simple whole number ratio. So this is not a whole number ratio. This 1 is to 1.5 is a decimal ratio, which is not possible. Now how can I convert this 1 is to 1.5 to a whole number? Okay, so I just multiply it with some other whole number. If I do into 1, I get the same ratio. So it's not a whole number ratio. So what I can do is I can just divide this into 2. So what will I get? 1 into 2 is 2. 0.5 into 2 is 3. So the ratio of iron to oxygen in this particular compound that we are speaking is in the ratio of 2 is to 3. What does that mean? We have 2 atoms of iron and we have 3 atoms of oxygen. So our empirical formula is nothing but Fe2O3. Next question. Calculate the amount of carbon dioxide that could be produced when 1 mole of carbon is burnt in air, 1 mole of carbon is burnt in 16 grams of dioxygen, 2 moles of carbon are burnt in 16 grams of dioxygen. So remember over here, to work out this question, basically we'll have to understand what is the reaction. So basically here, if you see, it's a reaction between carbon and oxygen. So carbon is reacting with oxygen to give you carbon dioxide. Okay, because it's given over here, calculate the amount of carbon dioxide which is produced. The first step here is, you see if your equation is balanced. So on either side you have 1 carbon and 2 oxygen. So here my equation is balanced. I don't have to worry about the equation. Okay. Also, what information am I getting from this equation? 1 mole of carbon reacts with 1 mole of oxygen, give me 1 mole of carbon dioxide. Okay. So the very first question is easily answered over here itself. Calculate the amount of carbon dioxide which is produced when 1 mole of carbon is burnt. So when 1 mole of carbon is burnt, you end up getting 1 mole of carbon dioxide, correct? So if you have 1 mole of carbon dioxide, how do you convert your moles to your mass? We know that moles is equal to mass by molar mass. So if I have to find out this mass, I can just multiply my moles into molar mass. Okay. So molar mass of carbon dioxide is nothing but carbon is 12 plus 2 into 16. Oxygen is 16. So I get 12 plus 32, which is 44 grams. So 1 mole of carbon dioxide is nothing but 1 into 44, which gives me 44 grams of CO2. So my first question is answered over here. Second question. What happens when 1 mole is burnt with 16 grams of dioxygen? If I look at this equation, C plus O2 gives me CO2, carbon plus oxygen giving carbon dioxide, and I calculate its masses. So 12 grams of carbon is reacting with 32 grams of oxygen to give me 44 grams of carbon dioxide, correct? Molar mass wise, if I see. Now, if at all, if at all this 12 grams of carbon has to react and give me 44 grams of carbon dioxide, I need to have 32 grams of oxygen. If at all this is decreased, then the amount of carbon dioxide formed will also vary. Such as in this case, we know molar mass of dioxygen is 32 grams per mole. But if it is reduced to half, then remember only 0.5 moles of it will be acting. 32 grams per mole is 1 mole, then half of it, 16 grams of dioxygen, will be 0.5 moles. If this is 0.5 moles, if you see this relation over here, I will end up getting 0.5 moles of carbon dioxide. 0.5 moles of carbon dioxide is nothing but 0.5 into 44, which is 2 grams. Similarly, if I want to try out my option C, I have 2 moles of carbon which are burnt in 16 grams of dioxygen. So from our second part B, we have seen that 16 grams of dioxygen is nothing but 0.5 moles. Okay. So again, if I see my relationship, I need 1 is to 1 is to 1 ratio for the proper action. Now if I have 0.5 moles over here, okay, If oxygen is 0.5 moles, irrespective of how much carbon is there, it will react 1:1 ratio. We end up getting only 0.5 moles of carbon dioxide, which is again 20 grams of carbon dioxide that is obtained. In other words, mass is equal to moles into molar mass, which is nothing but 82.0 to 0.1875, which I get 15.38 grams. Question number 5. Calculate the mass of sodium acetate CH3COONe required to make 500 ml of 0.75 per liter of the solution. Now here we are discussing a new formula which you have not still now, but it's a very important formula. Okay, so we have, whenever we dissolve a solute in a solvent, dissolve any powder in a liquid, make a solution, we need to know the concentration of that solution that we have. Okay? And there are different ways to express the concentration of the solution. Clarity, parts per million, have percentage mass. Like, so percentage mass means how much grams of that solvent solute is there in the solvent, total solution. Finally, when I speak about molarity, please make a note of this formula as we have not discussed this before. Molarity is nothing but moles of solute divided by volume of solution in liters. Remember, we are referring to the volume in liters. If it's given in ml, you have to convert to liters. So here, molarity is represented by capital letter M and its unit is moles per liter. Because here only you can see it is number of moles per liter that is there. Okay, so the minute you see moles per liter, remember it is molarity. Step number 1, let's calculate the moles of sodium acetate. So I told you molarity is, or M is equal to number of moles divided by volume in liters. So moles will be molarity into volume, correct? 500 ml is nothing but half a liter, so I write it as 0.5 liter. Okay, so if I just calculate 0.375 into 0.5, I end up getting my moles as 0.1875. Okay, now that I know the moles, what can I do? I need to find the molar mass of sodium acetate. So carbon is 12.01, hydrogen is 1.008, oxygen is 16.00, sodium is 23.00 U. So if I have to calculate, I have two carbons in my formula. So I will simply do 2 into 12.01 plus 3 into 3 hydrogens are there, 1.008 plus 2 into 16 plus 23. Okay, so I end up getting 24.02 plus 3.024 plus 32 plus 23, which is nothing but 82.0 grams per mole. Yes, I get a rounded figure of 82.0 grams per mole. Now, we know that moles is equal to mass by molar mass. So you see, the questions are very easy. They're just tricked for you because you will have to determine 2 to 3 things. So finding out your moles or finding out your molar mass is like the first step in most of your numericals. Make sure you all do it correctly and those concepts are clear to you all. Again, I'm telling, pause the slides as and when these concepts are repeating, because most of your numericals we are calculating number of moles, we are calculating molar mass. So pause the slide, do it yourself, and then forward and see if you have done it properly. Okay, so at the same time, please refer to our materials. A lot of such numericals are given to you all. Please go through those materials again and again, and if you'll have any doubts, we meet during our doubt clearing session. Let's discuss. So the 6th question goes like this: calculate the concentration in terms of molarity nitric acid, that is HNO3, in a solution which has a density of 1.41 grams per ml The mass percentage of nitric acid is 69% and the molar mass of nitric acid is 63 grams per mole. Now what are they asking you? They're asking you the molarity. So molarity we know is del M is equal to moles by volume in liters. Okay? And they have given you the density. So density is nothing but mass by volume, correct? Now density is 1.41 grams per ml. So if you convert it to liters, you do into 1000 if you express it in terms of the liter system. Okay, so I get 1410 grams per liter. So in 1 liter, basically my volume is 1 liter. My mass is nothing but 1410 grams. Correct? 1410 grams is nothing but so see, since the density is 1.41 grams per ml, okay, this is in 1 ml. So in 1000 ml, if I do it into 1000. So I get 1410 grams per liter, correct? So this is my density. Now, what I should see out of so many grams. Now, if my volume is 1 liter and my density is 1410 gram, that means my density is equal to my mass, right? So my mass is also nothing but 1410 grams. Okay. Now out of this 1410 grams, 69%, okay, this is the mass of my entire solution. 69% of this 1410 is nothing but my nitric acid. So let us see how much is that 69% of 1410. So what do I get? I get x divided by 1410 into 100 equal to 69%, or x is nothing but 69 into 100 divided, or x is nothing but 69 into 1410 divided by 100, which gives me 972.9 grams. So my mass of nitric acid is clear. How much mass is there? Now, from this mass, how can I calculate the moles? First thing is I need to calculate molar mass of HNO3. Okay, what is the molar mass of HNO3? It is 1 plus nitrogen is 14 plus 3 into 16. So I end up getting 63 grams per mole. Once I know the molar mass, once I know the mass, moles is nothing but mass by molar mass, which is 972.9 divided by 63, which is 15.44 moles. Okay, so concentration is what? Concentration of nitric acid, that is molarity, is nothing but moles divided by volume in liters. Now, since the volume is mentioned here and density is given in terms of 1 liter, we consider the volume to be 1 liter itself. So, molarity is nothing but equal to the number of moles, which is 15.44 mole. Question number 7. How much of copper can be obtained from 100 grams of copper sulfate? Okay, so it's very easy. The first step is to find the molar mass of copper sulfate. If X amount of copper sulfate has Y amount of copper, 100 grams of copper sulfate will have how much of copper? Molar mass of copper sulfate is nothing but 1 copper is there, 63.5 plus 32 plus 64, which is 159.5 grams per mole. So if I see the formula of copper sulfate, I know that 1 mole of copper sulfate has only 1 atom of copper. Right? So basically, 159 of copper sulfate will have 1 gram or 1 mole, which is 60 points of copper. Right? So if at all I reduce this 150.5 to 100 grams of copper sulfate, how much of copper is there? Just do a cross multiplication. 63.5 I will simply get 63.5 grams into 100 divided by 159.5, which is nothing but point. So, so totally from 100 grams of copper sulfate, I can obtain 39.8 grams of copper. Determine the molecular formula of an oxide of iron in which the mass percentage of iron and oxygen is 69.9 and 30.1 respectively. This is a similar question which we have got in previous, I think the fourth slide, okay. There they had asked you for the empirical formula. Here they are asking you for the molecular formula. Now remember, either way they have given you the mass percentage. So I just want you to pause and try this particular question by yourself. I can just guide you initially. First, what do? You consider the compound to be of 100 grams, okay? And then find the number of moles of iron, moles of oxygen. Once you found the moles of either of them, convert them into a simple whole number ratio and from there derive the molecular formula. See this table, mass percentage is 69.9 and 30.1. Atomic mass of oxygen is 55.85 and that of oxygen is 16.00. So if we find the number of moles, we get moles of iron to be 1.251 and that of oxygen to be 1.881. Now by dividing it by the lowest number, we get a ratio of 1:1.5. So we know iron to oxygen is in the ratio of 1:1.5. Correct? Now, since this is not a simple whole number ratio, we multiply it with 2. So when we multiply it with 2, I get iron to oxygen to be which is nothing but 2:3. So from here we get the empirical formula and the molecular formula as Fe2O3. Moving on to the next question, question number 9. Calculate the atomic mass. So here you have to calculate the average atomic mass of chlorine using the given data. So what they have given you, they have given you chlorine 35 isotope and chlorine 37 isotope. And they have given you the natural abundance of each of these isotopes. Okay. What you have to do is you have to find the average atomic mass. So I told you in our very first video lecture that when we speak about isotopes, it depends on their relative abundance, how much they are present in the nature. We take an average of them, okay? And then we calculate the average atomic mass. So basically what we have to do here is average atomic mass is nothing but you multiply its molar mass with its natural abundance and divide it by 100. So this formula again, I think this is the first time you're coming across the formulas. Kindly make it in your formula book. So I have M1, which is molar mass of my first isotope, chlorine 35, and its relative abundance, natural abundance, 75.77%. Similarly, M2, I have its, M2 is 36.9659 over here, and its relative abundance is 24.23%. So on a total, if I use the formula and just substitute the values, I get 34.9689 into 75.77 plus 36.9659 into 24.23. This into this into this. So here this is M1, this is A1, this is A2, this is M. Okay, divided by 100. So on substituting the values, I get 35.457 U. Now this 35.457 U, we put it up to significant figures after the decimal point. I can just write it as 30.6. Moving on to question number 10. 3 moles of ethane, C2H6, calculate the following. Number of moles of carbon, number of moles of hydrogen, and number of molecules of ethane. A very easy and straightforward question, but if you're getting confused, remember one thing. They have given you number of moles of ethane which you have. Number of moles which you have is 3. And in 1 mole of ethane, you know there are 2 carbon atoms. So if there are 3 moles of ethane, definitely you'll have 6 carbon atoms. So when it's 6 carbon atoms, you just need to calculate. You have 6 moles of carbon. Similarly, hydrogen, so you can calculate in the same way. Okay, see, one molecule of ethane has 2 carbon atoms and 6 hydrogen atoms. So since there are 3 moles of ethane, 3 moles of ethane will correspond to 6 carbon atoms, which is nothing but into 3, giving us 6 moles. 1 mole of ethane has 6 hydrogen atoms. So 3 moles of ethane will have 3 into 6, which is 18 moles of hydrogen. Okay. And number of molecules. Remember, 1 mole always corresponds to Avogadro number of molecules, which is 6.622. Number of molecules of ethane. Remember, 1 mole of anything, any element, any atom in has Avogadro number of particles. We'll discuss this in our second slide, which is nothing 6.0 into the power molecules. Okay. Now, if 1 mole has so many, 3 moles will have 3 times of this number. Okay, so 1 mole has how much? 0.022 into the power 3 molecules. So, how many molecules are there in 3 moles? 3 into 2 23, which gives me 1.807 into 10 to the power joules. Okay, remember I've tried to put this in the scientific notation form where it is n into 10 to the power n, where that n is between 1 and 9. Otherwise, I could also write as 18.07 something into 10 to the power 23. So the next question, what is the concentration of sugar in moles per liter? So remember, and if it's written reverse or it is written this way, it is the same. It is moles per liter, and in either way, it is representing molarity. Okay? If it's 20 grams are dissolved in enough water to make a final volume of 2 liters. So remember here, volume is given to you in liters itself, 2 liters. And what is the mass that is given? Mass is given as 20 grams. So it's a very straightforward question. Molarity we know is nothing but, they have asked you molarity, concentration in moles per liter. Molarity is nothing but number of moles divided by volume in liters. How to find the number of moles? First find the molar mass, divide the given mass by molar mass, find the number of moles. So kindly pause this slide and work it out, and then resume and see whether you get the answer, because we have worked out similar questions and it's a very direct question. So mass of this sugar, okay, C12H22O11 is 20 grams. Volume we know is 2 liters. So molar mass will be how much? It will be nothing but 12 into 12, which is mass of carbon, plus 22 into 1 plus 11 into 16. So I get 144 plus 22 plus 176, which is nothing but 342 grams per mole. Okay, now molar mass is known. How can I find my moles? Moles is equal to nothing but mass by molar mass. So I get 20 divided by 342, which is nothing but 0.0585 moles. Okay, now molarity is nothing but, I've told you, moles of solute divided by volume of solution. Remember, this is volume of solution, so you need to see the total volume of the solution and not just the solvent. Okay, be very careful. Volume of solution in liters. Okay. So that is nothing but 0.5 divided by volume they have given. Final volume is 2 liters by 2. So I get 0.02925 moles. Question number 12. The density of methanol is 0.93 kg per liter. What is its volume needed for making 2.5 liters of its 0.25 molar solution? Okay. So here, just see the question what is given to you. Density is given as 0.793 kg per liter. We can just convert this kg to grams. It will be 793 grams per liter. Second thing, they have given you total volume of the solution, which is 2.5 liters if it is having a concentration of 0.25 molar. Okay. Now, what are you supposed to see? Total is 2.5 liters. Okay, total water and methanol mixed. What should be the volume of methanol that you're taking? Okay, how can you find out the volume? We know that density is mass by volume, correct? Now, this is the volume that I need to find out because density is given. Mass, how can I find out? I have my molarity which is given. I have the volume. So, from molarity and volume, I can find out the number of moles that I have. And using moles and the molar mass of methanol, since of methanol is CH3OH, we can calculate thereby the mass. Okay, so let's see how it is done. So in my first step, density of methanol is 0.793 kg per liter. We know that 1000 grams is 1 kg. So again, if I have 0.793 kg, it will be nothing but 793 grams. Okay, so I've given it in terms of grams per liter, which is 793 grams per liter. Molarity is 0.25 moles per liter and volume is 2.5 liters. So molar mass of methanol, let us see, it is nothing but 12 plus 3 plus 16 plus 1. Correct? So I end up getting 32 grams per mole. Okay. How can I find my, using the molarity, how can I find number of moles? Okay, I know that molarity is nothing but moles divided by volume in liter. Correct? So I know molarity is how much? We have 0.25. So simply if I want to find number of moles, I can take this to the other side. So I have 0.25 into 2.5, which is nothing but 0.625 moles. Okay, so I found my number of moles. Now, how do I find this mass of mine? I know moles is mass by molar mass. So moles into molar mass gives me my mass, which is 0.625 into molar mass I have calculated as 32, which is nothing but gives me 20 grams. Okay, now I know the density, which is 793 grams per liter, equal to 20 divided by the volume. Okay, therefore my volume is nothing but 20 divided by the density, which is nothing but if 2 liters, which if I convert to ml, I do into 1000. Get 25.2. Hope it's clear. Again, question number 13. Pressure is determined as force per unit area of the surface. SI unit of pressure, Pascal, is shown below. 1 Pascal is basically 1 Newton per meter square. If the mass of air at sea level is 1034 grams centimeter square, that is in each centimeter square, it is 1034 grams. Calculate its pressure in Pascal. Now, slightly different question where you are mixing your physics and chemistry and trying to find out. So let's see how we can solve it. Okay. So what is given to us? We know that pressure at sea level is 1034 grams per centimeter square. Okay. First, what do we need to convert? We need to convert this to Pascal. We know Pascal is 1 Newton per meter square. Okay. And what is it? It is force per unit area. Force is nothing but mass into acceleration. Okay. All they have asked you is they have given you mass, they have asked you to convert it to Pascal. Okay. And Pascal is Newton per meter square. So if we find the force first, force is nothing but mass into acceleration. So whenever acceleration is due to the pressure of the earth, we call it as acceleration due to gravity, which is represented as g. Okay, now let's quickly see how we can solve this question. Okay, first thing is you convert your given mass into kilograms. Okay, so we know that 1000 grams is 1 kilogram, correct? So 1034 grams is nothing but 1034 divided by 1000, that is 1.034 kg per centimeter square. Okay? I am just trying to convert this from grams per centimeter square to kg per meter square. Instead of doing it in one go, I'm doing it in two steps so that it's easier for you all to understand. Okay. Now, if at all I have to convert it to this centimeter square to meter square. So I know that 1 centimeter square is nothing but 10 to the power minus 4 meter square. Correct? Why? Because I have 100 centimeters is 1 meter. Correct? So 1, 2, 3, 4. If I square this, okay, 10 to the power 4 centimeter square is 1 meter square. Or if I do the opposite way, 1 centimeter square is nothing but 10 power minus 4 meter square. So I can just write this answer as 1.034 divided by 10 to the power minus 4, which is nothing but 1.034 into 10 to the power 4 meter kg meter square. Okay. Now, how can I convert mass to force? Force is nothing but mass into acceleration due to gravity in this case, which is nothing but 1.034 into 10 to the power 4, and acceleration due to gravity is 9.8 meter per second. So I end up getting 1.01332 into 10 to the power 5 Newton meter square, which is nothing but 1.0. Question number 14. What is the SI unit of mass and how is it defined? Okay. So the SI unit of mass is nothing but kilogram. Okay. 1 kilogram is nothing but it is defined by fixing the numerical value of Planck's constant to be exactly 6.6260701 into 10 to the power minus 34 joules. So initially it was using this prototype. Further, they came up with Planck's constant and gave a method of calculations so that the precision reproducibility is same everywhere. Because this question number 15, match the following preferences with their multiples. So we know, we have our SI unit, and then sometimes we have our measurements which are being done, which are either in sub multiples or higher multiples of the unit we have. Suppose we are measuring distance. So a limited distance can be measured as meter. But if you have something very little, you have a scale and you're measuring, the size of maybe your book, then you're measuring it in terms of centimeter. So it's a submultiple. And similarly, if you're going for a distance from one city to the other, then you measure it in a higher multiple, which is a kilometer. So a basic knowledge of what these prefixes are and what multiples they represent is required for answering such questions. So to make it easier for you, I will give you the set of prefixes which are usually used for the multiples. Please make a note of it in your book, whichever you all write your formula, so that you all can refer and it's easier for you all. Okay. Deca, which refers to 10 to the power 1 or 10. Then we have hecta, which refers to 10 to the power 2. Kilo, kilogram, kilometer. So it is basically 10 to the power 3, 1000 times a meter, 1000 times a gram. Giga, which is 10 to the power 9. You have mega, which is 10 to the power 6. And then when we come to submultiples, okay, we have deci. So deci means divided by 10. So it is 10 to the power minus 1. Centi. Centi means 100 times less. So it's 10 to the power minus 2 centimeter we say. Milli. Milli is nothing but 1000 times less, that is 10 to the power minus 3. Similarly, micro is 10 to the power minus 6. Nano is 10 to the power minus 9. Pico is 10 to the power minus 12. And you have femto. So femto basically means 10 to the power minus 50. To the question, micro is there, it is nothing but 10 power minus 6. Deca is 10 power 1 or 10. Mega refers to 10 power 6. Giga refers to 10 power 9 and femto refers to 10 power 15. So if you know this list very well, these are the common ones which are used. So please write them in your notebook and make sure you all are referring to it on regular basis, because a lot of conversion also these will be helpful. Okay? So here are your answers. I hope the question is pretty clear to you all. Question number 16. What do you mean by significant figures? So we have discussed significant figures in our very first video lecture, right? So we have spoken that they are nothing but they are digits in a number which basically give you more idea about the accuracy, measured accuracy or precision which is there in your values. Suppose you have 0.0625 grams. Okay, so something you have weighed and it is of so many grams. Then remember, all your non-zero integers that you have, or your non-zero numbers that you have, digits, are your significant digits. The zeros which come before your non-zero digits are non-significant. If at all a zero comes in between your non-zero, suppose you have something like 101. So 1 and 1 are non-zero and a 0 between them represents a significant zero. Okay. Trailing zeros, that is zeros which are following your non-zero digits, are significant only if there is a decimal point. What do I mean? If I write 100, then these zeros are non-significant because I do not have a decimal point. But if I write 100.0, then all three zeros become significant. And if I write something in terms of scientific notation, n into 10 to the power n, then only this n is considered as a significant digit. This coefficient is not considered to be significant. Question number 17. A sample of drinking water was found to be severely contaminated with chloroform. So chloroform has a formula of CHCl3 and it is supposed to be carcinogenic in nature. That is, it is cancer causing in nature. The level of contamination was 15 ppm by mass. Okay, so ppm refers, I told you, we speak about concentration of any solution. I told we speak molarity, molality, speak about mole fraction. So ppm is also one term used for concentration, and ppm basically refers to parts per million. Okay, so what does it signify means whatever solute that you have is in a very small quantity when compared to a large amount of solvent. So in million parts or in 1 million, if you see by mass in this question, a million mass of that water or a million kg of that water will have 15 kg of your particular contaminant. 15 ppm, you have to express it in terms of mass. And the second question that they have asked you is determine the molality of chloroform in water. So molality is nothing but, remember, don't get confused with molarity and molality. Molarity, let's make a note of these formulas, is number of moles of solute in a liter of solution or volume of solution in liters. Okay, that's why we say moles per liter, and it is represented by capital letter M. Molality that we are speaking, okay, is nothing but number of moles of your solute, N remains as it is, in mass of the solution, mass of the solvent, sorry, not solution, in kg. Okay, so here you give moles per g and it is represented by the small letter m. So how do we go about with this question? Okay, make a note of the formulas which I have given you in the extreme corner, and let's see how we can solve them. So parts per million basically means how much of that is there in 1 millionth of it. So millionth is nothing but in 10 power 6. Okay. So express this in percent by mass. So what do you mean by 15 ppm? Okay. 15 ppm basically means, see, contaminant is chloroform, that we know from the question. Its level is 15 ppm by mass. So what does it mean? In 1 million grams of water, we have 15 grams of whatever chloroform that is there. Okay. Molar mass of chloroform, how can we find out? We have, so molar mass of chloroform is very easy to find out. See, we have 1 carbon, so 12 plus 1 hydrogen, 1 plus 3 into 35.5. So we end up getting 109.5 grams per mole. Okay, express this in percent by mass. So how can we express percentage mass? We know percent mass is mass of the solvent which is there, which we know is 10 grams, correct? Divided by total mass of your solution, which is 10 power 6 into 100. So basically 10 power 6 comes up, it becomes 10 power minus 6. So you get 15 into 10 to the power minus 4%. So moving on to how we can determine its molality. Molality, I have already given you the formula. It's number of moles of your solute divided by mass of the solvent in kg. So how can I calculate the moles of chloroform? Okay, number of moles is nothing but given mass divided by molar mass, correct? So my given mass is nothing but, in this case, if you see, my given mass is 10 grams divided by molar mass, which is 119.5 grams. In the very first step we have calculated. So on dividing, I get my number of moles to be 0.126 moles. Okay. Now, how do you find mass of the solvent? Okay. Assuming solute mass is negligible in comparison, mass of water is nothing but 10 power 6 grams that we have. Okay, since our solute is very negligible, we are not adding it. It's like, you add one crystal of salt in a glass of water. It will not make any difference to the mass of water. Okay. Now, 10 power 6 gram, if I have to convert it in kg, what do I get? I know 1000 grams is 1 kg, correct? So 10 power 6 grams is how many kg? I just do the unitary method, I get 10 power 6 divided by 10 power 3, which is 1000. We get 10 power 3 kg. Now let's calculate what is our final molality. Molality is nothing but moles of solute 0.1256 divided by mass of solvent in kg, which is nothing but 1000. So I can write this as 0.1256 into the power minus 3, because here it is 10 to the power 3. When it goes to the numerator, it becomes 10 power minus 3. Or if I'm denoting it in terms of scientific notation, I take my decimal to the right hand side. So I put 1.256 minus 4. Unit is mole per g. Or number 18, convert the following to scientific notation. Scientific notation, I have already told you all, is a representation in the decimal form, which is n into 10 to the power, where this n represents any number between 1 and 9, and the small letter n can be any integer. So it can be positive or it can be negative. So if you're, in other words, if you're moving your decimal for your reference, okay, this is my left side, this is my right hand side, correct? If at all you're moving your decimal towards the right, then you get a negative integer. If you move your decimal towards the left, then you get a positive integer for n. So representations are pretty clear over here. You all can try it by yourself and then cross check the answer. So over here, if I have to get capital letter N, I have to transfer my decimal towards the right hand side. So I transfer it by 1, 2 and 3 places. So I get 4.8 into 10 to the power minus 3. Similarly in 234,000, I have my decimal after the zeros. So I am getting it towards my left hand side. So 1, 2, 3, 4, 5. So I get 2.34 into 10 to the power 5. Similarly, 8008 also, I have my decimal after the 8. So I move it by 1, 2, 3 places. So I get 8.008 into 10 to the power 3. And the last 500.0, I will move my decimal from 1 to 2 places. So I get 5.000 to 10 to the power 2. Okay, so remember, whenever I have moved it to the left hand side, I have taken that positive integer fine. When I move it to the right hand side, it basically means I'm dividing it. Okay, so here you can see it in this way. 10 power minus 3 means I'm dividing by 1000. Okay, so 4.8 divided by 1000 will give me 0.0048. Okay, 10 power 3 in this case means I'm multiplying. So it is 8.008 into 1000, which is 8008. 6.022 into 10 power 23 is already in form of a scientific notation. They can also ask you to represent it as standard form. So remember, since it's a positive integer, your since it's n is a positive integer, your decimal has moved towards the left. So what it basically means here is it is 6.022 into 10 followed by 23 zeros. If you multiply, you get 60000. So just see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, 23. So this is basically your Avogadro's number. Okay? They can ask you represent in standard form also, so you'll have to know how to convert from your scientific notation to standard form, as well as convert from standard form to scientific notation. Question number 19. How many significant figures are present in the following? The significant figures, I told you, they give you good information about the accuracy in your measurement. Okay. Again, let's quickly have a recap of what figures are considered significant. Okay. Leading zeros are not significant. So zeros before your non-zero digits are always not significant. Captive zeros, that is in between your non-zero digits, are always significant. Trailing zeros after decimal are significant. Trailing zeros without decimal. So trailing zeros are zeros which follow your non-zero digits. If at all there is a decimal, then they are significant. If at all there is no decimal, then they are considered non-significant. And in scientific notation, where you write n into 10 to the power n, only n represents your significant figures. Okay? So with this in mind, please try to do this numerical by yourself, because it's very direct and you may not believe this is where we actually get confused. Okay, so do it by yourself, resume the video, and then see whether you get the right answer. Okay? So 0.0025, if you see zeros which are leading zeros, so 0, 0, 0, 3 zeros are leading zeros, we can't consider them as significant. So only 25, so you have two significant figures. In 208, we have 1 0 between it, which is a captive zero. It's in between two non-zero digits, so you have three significant figures. Similarly, in 5005, we have four significant figures. In 1,26,000, if you see, we have trailing zeros, okay? But these zeros do not have a decimal, hence they are considered non-significant, and we have three significant figures here. Okay? Similarly, 500.0, if you see, since there's a decimal, this zero becomes significant, and in between two significant figures, if there are zeros, they are again considered significant. So you have four significant figures. Question number 20. Round up the following up to three significant. So we have discussed the rules for rounding up of significant figures in the very first video. Please refer to it if you have forgotten, but a brief reminder. With all the digit next to the digit that you're rounding up is greater than 5, then you round it up to the next digit. Suppose you have something like, in this first case, 3, 4, 2, 1, 6. So up to three significant figures means it's 3, 4, and 2. So after 2, you have a digit which is lesser than 5. So when it's lesser than 5, you leave this 2 as it is. But if at all it is greater than 5, if this was 6, then you round off your 2 to the next digit, which is 3. Okay. And if at all it is equal to exactly 5, then remember, you leave the digit as it is if it's an even digit, and if it's an odd digit, you convert it to the closest even digit which is there. So with this in mind, let's quickly solve this question. 34.216, if you see, up to 3 significant figures, if you see, we have 3, 4 and 2 which are our significant figures. So after 2 that we have 1 and 1 is less than 5. So there is no change in what answer we get, and the rounded off figure is nothing but 34.2 itself. Similarly, in 10.4107, our 3 significant figures, first 3 significant figures are 1, 0 and 4. So after 4, I have 1 again, which is less than 5. So my number remains as it is. I rounded off, there is 10.4. Third one, 0.04597. So again, my leading zeros are non-significant. So my first 3 significant digits will be 4, 5, and 9. So after 9, if I see, the next digit is 7, right? Since 7 is more than 5, I have to round up my 9 to the next digit, which becomes 10. So when it becomes 10, I get 0 here and a carry forward over here. So I get answer as 0.460. It's clear. Okay. Similarly, see, we retain the trailing 0 here to preserve 3 significant, because we need 3 significant digits away. That's why I'm keeping the 0 as it is. Okay. 2808. So again, the first 3 significant figures are 2, 8 and 0. So after the 0, I have a digit which is greater than 5. So next digit is 8, which is greater than 5, correct? So I round up my number as 2, 8, and the 0 becomes the next number, 1, 0. The following data are obtained when dinitrogen and dioxygen react together to form different compounds. Okay. So mass of dinitrogen and mass of dioxygen. Dinitrogen is nothing, don't get confused, okay? N2. Dioxygen is O2. 14 grams reacts with 16 grams. So 1 mole, because N2, if you see atomic mass, 1 mole of nitrogen is 14 grams. Again, 14 grams reacts with 32 grams. So 1 mole is reacting with 2 moles of oxygen. Here you have 2 moles of nitrogen reacting with 2 moles of oxygen, and again 2 moles of nitrogen reacting with 5 moles of oxygen. Okay, so what is the question we have asked is, let's see. The oxygen combining with fixed mass of nitrogen, that is 14 grams. Convert third and fourth to base nitrogen equals to 14 grams. So here you have 28 grams is reacting with 32 grams in case 3. In case 3, if you see, you have how many grams? You have 28 grams reacting with 32 grams of oxygen, correct? Now they are telling, instead of this 28, if I have 14 grams, how much of oxygen will it react with? So it is definitely, it's a very straightforward thing. It is nothing but 32 into 14 by 28, 32 by 2, that gives me 16 grams. Okay. Question number 2, fourth one. If I have 28 grams of nitrogen reacting with 80 grams of oxygen, how much will 14 grams of dinitrogen react with? So again, it's the same thing. 80 into 14 by 28, which gives us nothing but 1, 2, 40 grams. So very straightforward question. You don't have to break your head. See, they give you a lot of data to make sure that you feel it's a difficult question. Try to understand the questions. Okay, they are very straightforward in your competitive exams. Let's just again see the explanation of this answer in the next slide. Okay. So first you need to find the ratio of oxygen. So in the 1, 2 and 4 case, if you see, you have combining mass of oxygen is the same, which is 14 grams, with 16 grams, 32 grams and 40 grams. Okay, so if you simplify the ratio, you get 1 is to 2 is to 2.5. Since 2.5 is not a whole number, we multiply it with we convert it to a whole number ratio. So now if you see, you get the ratio as 2, 4 and 2 is to 4 is to 5. Okay, now which law does this actually, obey? The above experiment, if you see, is obeying the law of multiple proportions. The reason is, you have a fixed mass of nitrogen, which is 14 grams, which is reacting with different masses of your oxygen. So in the first case, what happens? You have 1 is to 2. So you get NO2. In the second case, what do you get? You get NO4. The The third case you get, 5. Okay. So fixed mass of nitrogen is reacting with different masses of your oxygen, and the ratio of oxygen in all three cases is a simple whole number ratio. Moving on to the next question. Fill in the blanks in the following conversions. So here you have conversions. If you refer to the material which I have given you previously as well as our Achievers Hunt material, you will have these conversions written in them. I'll anyways explain how do you convert them. Okay? So 1 kilometer is how many millimeters, which in turn is how many picometers. Okay, so we know that 1000 millimeters makes up 1 meter, correct? And 1000 meters is 1 kilometer, right? So in case I have to find out 1000 meters is 1 kilometer, so 1000 into 1000 meters is how many kilometers I get. Okay, so it is nothing but 10 power 6 millimeters that I get over here. Okay, 1000 into 1000 millimeters is 1 kilometer. Here it becomes 10 power 6 millimeters. Similarly, how do I convert it to picometer? Okay, now 10 power 12 picometer is 1 meter. So if I'm looking at 1000 meters, which is 1 kilometer, it how many picometers? So I get 10 power 12 into 10 power 3, which is nothing but 10 to the power 12 plus 3, that is 10 to the power 15 picometer. Okay, so our first answer is explained. Similarly, let's see the next one. Okay, now in case of the next one, 1 mg is how many kg? Okay, here it gets a little tricky. Okay, so from smaller unit, when you're going to the higher unit, how do we consider? Now we know 1000 grams is 1 kg, correct? Or in other words, if you have to say 1 kg is nothing but 10 power 3 grams, or 1 gram is 10 to the power minus 3 kg, correct? Now, in the other way, we have milligram. So when it comes to milligram, we have 1000 mg is 1 gram, or in other words, 1 mg is 10 to the power minus 3 grams, correct? Now, if 1 gram is 10 to the power minus 3 kg, then 10 to the power minus 3 grams will be how many kg? So you get nothing but 1 gram is 10 to the power minus 3 kg, then 10 to the power minus 3 grams, which is nothing but 1 mg, is how many kgs? So you get 10 to the power minus 3 into 10 to the power minus 3, which is nothing but 10 to the power minus 3 plus minus 3, which is 10 to the power minus 6. So I hope this is clear to you. Let's see the second conversion where we have to convert this. Now we know 1 mg is 10 power minus 6 kg. How do you convert mg to nanogram? Okay, so we know that 1 nanogram is nothing but 10 to the power minus 9 gram. Similarly, 1 mg is nothing but 10 to the power minus 3 grams. If I have to convert this to nanograms, I can get nothing but 10 to the power minus 3 into 1 divided by 10 to the power minus 9, 10 to the power 6 nanograms. So I get 10 to the power 6 nanograms over here. Okay. The second question is also done. Again, 1 ml is how many liters? So we know 1000 ml is 1 liter. So 1 ml is nothing but 10 power minus 3 liters, which is nothing but 0.001 liter. And liter and dm cube is the same, so it will be the same answer. Okay, the last question in this particular video lecture. If the speed of light is 3 into 10 to the power 8 meters per second, calculate the distance covered by it in 2 nanoseconds. Okay, so this is a slightly physics-based question, but again, it usually involves the conversions of SI unit. That's why they have given it in terms of chemistry. Okay, speed is nothing but distance by time. Physics we present speed as v. So initially, definitely distance will be nothing but speed into time. So we have a formula. Speed of light is nothing but 3 into 10 to the 8, and time should be in seconds. So they have given you 2 nanoseconds. 2 nanoseconds basically means 2 into 10 to the power is 9 seconds. So distance will be 2 nanoseconds is 2 into 10 to the power minus 9 seconds. Okay. Distance is nothing but 3 into 10 to the power 8. 2 into 10 to the power is 9. So 3 2s are 6 into 10 to the power 8 minus 9, which is 6 into 10 to the power minus 1, or you can write it as 0.6. So with this, we have come to the end of our exercise question and answers part A. We have our exercise question and answers explained in part B, which will be continuing after this video. So meanwhile, we request you all to go through our study material and our quizzes and our detailed prepared notes. So you can see in our videos also how in detail we are trying to cover your syllabus so that you're well prepared for your competitive exams and your concepts are crystal clear. We request you from your end to go through the study material so that only when you go through you get doubts, and when you have doubts we can make our doubt clearing session more interesting. So till then, keep studying, keep learning, keep growing. Take care. Bye.